Hello, and welcome to AI for Mechanical Engineering. In the previous course, we've learned how to solve optimization problems and apply this to machine learning through a technique called gradient descent. In today's lecture, we'll be looking at some basic examples in solving optimization problems. Now, the first example is linear programming. Linear programming is a mathematical technique that finds the best solution to a problem by either maximizing or minimizing a linear function given a set of constraints. Here, note that both the objective function and the constraints are considered to be linear, and one important property is that this linear problem is also considered to be convex by definition. So if you recall the definition of something being convex, the interpolation of these values should always be greater than or equal to the function within that region. Now the same applies to any given linear function, where in this case, you can see that the equality condition holds true, which in turn implies that the problem is convex. Now, in order to solve this linear programming problem, the first approach is to visually solve the problem. So assume we're given this objective function, and if we set this objective function to some constant and collect all the possible values that satisfy this relationship, we end up with parallel lines within the domain. And because we have this set of linear constraints, if we represent the feasible region of the optimization problem, we have this following box. So from a geometric standpoint, the problem simply becomes to find a line that intersects with the feasible region, but at the same time has the largest y-intercept. And because we have such a simple problem, we can see that this value has the largest y-intercept, which in turn implies that the optimal solution is at this point. The second way to solve this problem is to use a module known as CVXPy, which is something I've mentioned in the previous lecture. So given the same optimization problem, the first step is to represent the optimization problem in something known as the standard form. Now this representation uses vector representations, which is why the objective function and these constraints are represented as vectors and matrices. Here, we collectively represent these lower and upper bounds in terms of these vectors over here. So this becomes our lower bound, and this becomes our upper bound. And again, if we collectively represent each the lower bounds and upper bounds of the optimization problem, we have these two vectors. Now, once these elements are defined, we can write them out as variables in Python. So first of all, we have our F matrix or vector over here, and then we have our lower and upper bounds that we've previously defined. And X is simply a placeholder for the optimization problem, so we define the shape of the variable. So 2 by 1, which shows that we have something in this form. And finally, we solve the optimization problem using the function cvx.minimize, and we represent the lower and upper bound using the following line. As a result, we end up with the optimization results, which are solved numerically. So x optimal is 2 and 3, which is identical to the previous method. And because we've represented the optimization as a minimization problem by adding a minus sign up front, our intercept becomes minus 10.5, which is 5. So this was an example to show how we can solve a very basic optimization problem, in particular linear programming. The next form that we'll be looking at is the quadratic form. Now this quadratic form is more commonly used in optimization problems, and I've previously mentioned this quadratic form when we've solved for the optimal solution in the gradient descent case. Just to reiterate, the quadratic form represents a function in terms of vectors and matrices. So here we have x, which is our column vector, and its transpose self, so these are vectors. and H, which essentially is a coefficient matrix. Now, each element of H, shown over here, is a representation of how each X pair interacts. And as we've seen in the example from the previous lecture, we can solve for the solution relatively easily using this quadratic form. And based on this form, we can define something called quadratic programming, which is essentially solving an optimization in quadratic form. So just like we did for the linear programming case, we'll be representing a given optimization problem in its standard form. And here we have the objective function in quadratic form. Note that x corresponds to our variables, x, y. And here we have two additional components, where the first corresponds to the inequality constraints of the optimization problem. And the second corresponds to the equality constraints of the optimization, represented as a system of equations. And finally, we have our lower and upper bound for the constraints. Now, before I move on, you'll notice that in the inequality constraints case, we have this less than or equal to sign. Because we have a greater than or equal to sign in the constraints, we can simply represent this by flipping the signs of that inequality equation. In other words, we have the following expression, which allows us to collectively represent all three of these inequality constraints with a single matrix and vector. Now let's take a look at actual examples. So first of all, let's assume that we're trying to minimize the distance between some arbitrary point that falls within a feasible region. And our goal is to minimize the distance between that arbitrary point and the given point over here. The first step to solving this optimization problem is to model this as an optimization problem, meaning that we need to define what the objective function and our constraints are. So because we're trying to minimize the distance, this becomes our objective function, which is derived from this term over here, and our constraints are given as the following. Now, although we can solve this graphically because it's a very simple problem, here we'll be using CVXPy to solve the optimization problem. Now we first start off by representing the problem in quadratic form. So first we expand and rewrite the optimization problem in terms of its quadratic form, which is the following. And here, as you can see, you'll notice that we have our H matrix defined as the following, our F transpose, and our constant term C. Next, for the inequality constraints, because we only have a single condition, this becomes our A matrix and our B value. And finally, because we only have a lower bound and no upper bound, we have all of our components defined for CVXPy to solve. Based on this information, we can finally plug in the values, define our F, H, A, B, and lower bounds, and simply solve for the optimization problem by using cvx.minimize. And finally, when we solve for the value, you can see that we have the following solution, and this corresponds to this point over here, which also graphically makes sense in terms of the optimization problem. Now for the second example, let's assume that we're trying to start at point A and then pick up some water with a bucket along the riverside and then deliver it to point B. Mathematically speaking, we're trying to find the point along this line that minimizes this distance and this distance. So if we model this and represent this as an optimization problem, our objective is to minimize the norm of this vector plus this vector. In terms of the constraints, you'll notice that the point that we're looking for always has to exist along this line where x2 is equal to 0. So if we represent this, x2 is always 0, meaning that writing out ax equals b, which corresponds to our equality constraint, we have 0, 1, the following. Now, one additional thing to consider is in real life, when we're traveling with a bucket full of water, it usually is harder for the person to travel, meaning that putting equal weights on both of these distances would be less plausible. Hypothetically speaking, if we want to put more emphasis on traveling less distance with a heavier bucket, we can use this weighting term, mu, in front of here to represent the fact that each distance should not be considered equally. So using this modified form of the objective function, we can write out our new objective function as the following, where mu is a term that puts weighting on the second distance. So here we're assuming that both coordinates are given for point A and B. And because we've already defined our equality constraints, all we simply have to do is use cvx.minimize to solve for the optimal solution. And as a result, you can see that cvx_pi returns the optimal solution for this problem. Now here in this example, we've set mu equal to 1. However, if you'd like to put more emphasis on the second part of the travel, or d2, feel free to change the value of mu and see how the optimal value changes. And finally, we have the supply chain management optimization problem, which is a problem where the goal is to find a point that minimizes the sum of transportation costs between 3 given points, which essentially can be seen as an optimization problem where the goal is to minimize the distance from all 3 points. So similar to what we've done in the previous example, we can formulate this problem as minimizing the norm of all 3 vectors. So assuming points A, B, and C are already given, our objective function simply becomes the sum of all norms. And one thing to note here is that although we're using the 2 norm in this case, we can also use the 1 norm to represent the distance between these points. Now this also can be considered a convex problem. However, I'd like you to think about why this is the case. And in this case, because we don't have any constraints, if we solve for the problem, we get the answer over here. So in today's lecture, we've looked at a couple different ways to look at optimization problems so that we can get used to solving these optimization problems. And we've also looked into a method using cvx_pi, which is a module in Python that we can use to solve these optimization problems. Unlike the examples that we've seen for gradient descent, in these examples, we've learned how to solve these constrained optimization problems. This is the end of today's lecture, and thank you.